Hi, we're here at the Ultra-Fast Photonics Lab at the University of Toronto to do a demonstration of the virtual reference analyzer for the measurement of a short-length patchcord cable. We're using a sacrificial APC to APC, or FCAPC to FCAPC patchcord between the DUT port and the device under test in order to minimize damage to the connectors within the device. So what we're going to do is we're going to place our device under test on a table, and we're going to open up the software, and we're going to set our start wavelength at 1510, our stop wavelength at 1640, our output power at 3 dBm, and we're going to ensure that the virtual reference analyzer is connected to the tunable laser through GPIV by clicking on the drop-down menu, selecting refresh, then clicking on the drop-down menu again, and you'll see that your laser has shown up automatically. The GPIV port of the laser has shown up automatically. Select that port, and we're going to select our tunable laser mainframe as the 8164B, because that's what we're using here. This is an 81600B series tunable laser. We're using option 160. It's from Agilent Technologies, and the mainframe is an 8164B mainframe. So we're selecting 8164B, and the number of points we're going to leave at 50. We're not using compression. We'll demonstrate compression at a later date, and then we just simply click scan. So the scan is about 13 seconds because we're scanning at 10 nanometers per second, 130 nanometer bandwidth. So once the scan is complete, there's roughly 2 to 3 seconds. You'll start to see the raw scan pattern show up on your screen. Some of the important things, what you can do once you have the raw scan pattern, is that there are cursors at the bottom to increase or decrease your bandwidth any way you like. So once it shows up, click OK. And we're moving on to the next step. This is an automatic balancing step. It's not necessary to do it, but it's just if you like to do balancing. So at the top you see the power spectrum. This is an FFT, or the power spectrum of the raw scan pattern. And we're using this to find the reference, the length of the virtual path that will balance the group delay in the device under test. Okay, because that's how we're balancing the system. So if you change the number of points, you increase or decrease the resolution of that balancing. Now this would be when you move the number of points in the power spectrum. That's the it's not a fine balancing. It's more of a coarse balancing. The manual balance at the bottom is more of a fine balance. So increasing the sensitivity would allow us to to vary that path length more when we click the cursor. So we're going to move that central wavelength from here. We're going to move it further. So if I increase the sensitivity, and now I increase my virtual path length. I've moved now my center here, so I moved it too far. I'm going to move it, reduce my sensitivity a little bit, and move it here, and we should see it in the center. So now that I've centered and balanced the interferometer virtually, I'm going to click on OK. And the next step is the fit. So if we increase the fitting parameter, we just increase the contrast of the fringes. Okay. So what we want to ensure is that we only have one peak point and one valley point for every peak or valley on the interference pattern. So we've balanced, we fit, and now we just press OK, and the system will calculate everything by itself. It's going to calculate the balance point. It automatically did that just now. Then it's going to calculate where the minimum point is and the maximum point. And what I mean by that is that it's going to move the center to one side of the bandwidth and then move it to the other side of the bandwidth. And it's going to calculate what the minimum is and what the maximum is, so that you have two peak points on each side of the center, the central wavelength, this middle the largest hump in the interference pattern. So once that has completed, you see the results. The results, you have the group delay, group velocity dispersion, and the dispersion length. The dispersion times the length parameter. So we've got our group delay, our group velocity dispersion, and our dispersion length plotted. If you like to save the scan, and we're going to do that right now, you simply click Save Scan. Okay? And this is going to save the raw interference pattern that we first did when we scanned. It's the raw Fabre-Perot interference pattern. And you can save that, and at a later date, you can always go back to this experiment and change the number of points that you produce. So this time we produced 50, perhaps next time we want to produce 500. So we can always go back and produce more points at a later date. So if we press Save Scan, the system will bring up a menu, and we'll save this scan as a scan, we'll call it scan 1 for now. Okay? Press Enter, and the system will have saved the scan. You can always export the results from this current experiment if you like. It exports to a file with no extension. You can always add .text, and then you'll be able to open it up in Notepad. Or you can import it into Excel or any MATLAB if you like. So again, thank you for watching, and we'll hope to see you again next time.